Yeah, so I came across this thing called Pick's theorem, which says that for a shape like this, can you see my screen?
Yes.
Okay. So for a shape like this, any shape that we can make on a geoboard, we can get the area of the shape by just counting the points on the perimeter, on the border, and the points inside. So it says that area is equal to I plus p by 2 minus 1. I is number of these dots which are inside.
Mm.
P is number of the dots which are on the perimeter. Yeah, so half the count of the points on the perimeter plus the count of the points inside less 1 will give the area of the shape. So I, like any shape you can make, like even weird shapes, like I don't know, I guess we could make like a star shape, or okay, it should not cross, right? Okay, whatever weird shape you can think of, okay, like this
Mm.
maybe,
Mm.
it's supposed to work for all shapes
Okay.
that we can make on a geoboard.
Can we all discuss together and work on? Yeah.
Yeah.
So I am thinking of starting with different rectangles
Huh.
and maybe prove it for rectangles first.
Okay. Yeah. That was also on my mind. And I also wanted to go to triangles because polygons can be composed of triangles. Yeah, but rectangle seems to be the simplest place to start. Right? Yeah. Will it work for all rectangles?
Mm.
So if we consider this rectangle to be some a by b. So here it is 1, 2, 3, 4, 5 by 3, but can we show it in general for a by b?
So I am thinking in terms of induction. So
Mm.
it works for the square with just side one.
Okay, yeah.
Now imagine that I'm increasing the length by one.
Hmm.
Okay, so basically I'm just using induction. That is, if it is true for L cross B, I am trying to show it is true for L plus B, L plus 1 cross B and L cross B plus 1.
Oh, okay. Uh, we can do it algebraically also for a rectangle.
Yes, I mean, so that's what eventually I'll do. So it's like,
Okay.
suppose I have an L cross B,
Mm.
I am going to increase the length by 1.
Mm.
So now that means the area is going to increase by B.
Yes.
So if I am going to increase the length by 1, uh, B minus 2 will become interior points. That is, points which are
Correct.
on the perimeter will become interior points. So
Correct.
if I'm adding B minus 2 and the interior part.
Yes.
And the perimeter, it is like,
2 extra points get added. Ashwin, you were saying that we can start from unit square. So here it is 0 plus 2 minus 1, which is 1. So it holds for this. And if I increase the length, Ashwin, you were saying?
right. So, yeah, so I am looking at a rectangle of L cross B and I'm increasing the length by 1. So assume that this is the rectangle that you're starting with, and now, yeah, maybe just use a different color, blue color rubber band, just to add that extra portion. Uh, so now what happens is, when I'm extending this rectangle by 1 unit, I am basically adding an area of B.
Yes.
So now in this theorem, I'll just see how the interior and the perimeter points are changing.
Mm.
So yeah, maybe I'll just give like a minute for everyone to work it out. I'll also like work it out.
A was the original length, kya, Ashwin? A is the.
I am treating it as L. So L and
Oh.
B.
So if it works for a rectangle of size L by B, can we show that it will always work for a rectangle of size L plus 1 by B? Like generically, not for a specific rectangle, but in a generalized fashion, can we say it will work for L plus 1 by B? That's Ashwin's question he has posed.
So for here, every unit measurement, we have to consider 1 point and then plus 1 point at the end. It's like for one side, if at all I'm considering for every unit measurement, if it is 3 centimeters, it's 3 plus 1. Like if at all I want to prove this in some way.
Yes.
Oh, basically, how many unit length is this? So many, this is one, right? We don't even have to look at the points. If you look at the perimeter, how many unit lengths of perimeter is there? That's the same number of points on the perimeter.
Yes,
Correct.
correct. Correct. So perimeter will be equal to the number of points. Yes. Number of points P.
Okay, so one thing that I'm seeing is it only works for it won't work for a line because line has area as 0 in geometry. Suppose if we look at a line and the Pick's theorem, because suppose if we take the length just as 3 units with 4 points, then 4 by 2 is 2. 2 minus 1 is giving us 1 unit square, which is obviously not the area of the line. So it is only working for flat surfaces.
Yeah, it's for polygons.
Polygons.
Basically closed figures, right? Fixed theorem is
Closed
closed figures.
Closed figures.
Closed figures, yeah. Lines, I don't think is applicable here. Yeah.
Yeah, it's not applicable to lines. Yeah, I was just going one step below.
So when we increase the length by 1, the inside points are increasing by B minus 2. And the perimeter is increasing by 2, that's it. Is that right?
The inside points is increasing by what did you say?
B minus 2. I think I'll make this a bigger.
Why will it be B minus 2? 2 B. B is the number of points, Gauri, or is it number? Is it just the length?
Breadth.
It is a breadth, right? I mean, it is the. So it is 3 in this case, no? It is not 4,
Correct.
no?
Correct.
So I think it's like when you increase the length by 1, the number of interior points increases by B minus 1.
B minus 1.
Like I also thought it was B minus 2, it should be B minus 1.
How?
So here you are having, for example, this
These 2 points.
and breadth 3, right?
Right.
So basically now you are adding 2 extra points.
Oh, right. Because it's the number
So
of
yeah,
points.
earlier I was like doing 4 minus 2, it should be 3 minus 2.
Correct.
Now it works.
Yes. So if it works for rectangle, then I think we can take a right triangle, which is half of this rectangle.
Instead of increasing by 1, you can increase by some x.
Yes, we have not yet done that.
So what is the nature of x? Nature of x has to be a positive integer, or it can take any natural number.
Yeah, we will assume x is a positive integer only. So it's like now we will, okay, instead of increasing by 1, we will increase by some x.
Okay, got it.
So it should still hold. You can like algebraically show that it's still, the formula still works.
We are increasing it by 3 units, for example. In first case, we increase by only 1 unit. But if we are increasing it by 3 units, then the number of points is increasing by 6 from the original figure. 3 units, one more. Right, 6. So in this case, it is clearly not b minus 2 or any, we'll have to figure out something else. So
Huh.
it will not be, so maybe b minus 2 multiplied by 3 or something like that. Maybe it will be. It is b minus 2. So that is maybe, yeah. B minus 2 is 1. 1 multiplied by 3 is 3. So it's not, the points are increasing by 6 in this case.
You mean the points on the perimeter?
No, inside.
Oh, inside.
That's what we were talking about, right? We were talking about the number of points inside, no?
Like both inside and on the perimeter. So, yeah, inside points, it should be what?
Increasing by 6 now.
Whatever x you are increasing.
So the x was 3 in this case. We increase the length by x, that is 3. B minus 1 times 3, right? That will be the formula in that case. B minus 1 times x.
So the interior points will increase by b minus 1 times x, and the perimeter points will increase by 2x.
So what are we doing now? We are now looking at whether it works for any rectangle, is it?
Yes. So I think we are able to see that the formula is true even if we increase the length by any positive number. So I think that in fact implies that it is true for all rectangles.
Yeah, the increase in area in this way is also bx. And we know from our area formula that increase in area is in fact bx. So we can see this holding. Okay, so since this works in one direction, like if we are changing both length and breadth, it's just a matter of doing it in one direction first and then the other direction. So we are covered for all rectangles. Holds for all rectangles. Should we look at right angle triangles now?
Yes.
So what is the new area that you're getting after you put in the formulas? Is it I plus xb plus p upon 2 minus 1? Is that what you got?
Plus p by 2 minus 1. Yes.
I plus xb plus p by 2 minus 1, right?
Correct. And we know that the original area was I plus p by 2 minus 1. So the
Correct.
increase in area is, according to Pick's theorem, the increase in area is bx.
Bx.
And we know from
which is
our...
actually, correct.
Yes.
Correct.
Yeah.
What Pick's theorem is also saying is that area of any shape in the geoboard will be like an integer or it will be something half. You can never get a shape with area 2 by 3 or any other fraction.
Yeah, it will always, it will either be half or 1. It will not be any other number, right?
Yes.
Correct.
No, I can make this square. Oh, that will be 2.
No, if you look at the formula itself, no, see, all of them are whole numbers, Gauri.
Yeah.
I think by looking at right angle triangles, we can like get it.
So if I take a rectangle and split it into 2 like this, is the p and I distributed evenly always? 1, 2, 1, 2, 2, 1, 2, 1, 1. What about this one? So will the points on the perimeter, so we know that by drawing this diagonal, we are cutting the rectangle into 2 halves.
Correct.
Are we also splitting, I mean, getting an even split of points inside and points on perimeter?
Points on perimeter equal split is actually correct, except for the fact that we need to ignore the points that is forming the diagonals, because you are actually double counting it.
Correct.
Even in the corners, right? Yeah, anywhere on the diagonal actually.
Anywhere on the diagonal, right. I is also working out because area is same. Is that enough? Oh, but we are trying to go to area same. So if we were to take the same approach of say increasing the base or the height. So here base is increased by 1.
So if you are increasing the base by 1, you are not increasing any points inside.
So
At least in this
sometimes,
particular case. In this particular case, it may not happen in all the cases, but the number of points remain the same inside.
no,
Height.
we are increasing by 1, right?
Yeah, base.
No, the interior points, we are adding 1 interior point at least.
How? Look at the green triangle. Gauri has made 3 triangles together, right? Green, blue, and orange. Look at the green triangle, which is the smallest right now, in that particular example. Green one, it has got only 1 interior triangle, right? 1 interior point, no?
Yeah, so the first one, yeah, this has got
Red. Look at the red one. Red one has got 1 point inside. And the blue one also has 1 point inside.
Oh, okay.
But orange has 2 inside.
But the orange one has got 2 points inside. So we are increasing.
So I am looking at the small triangle that is at the bottom. That is the triangle with base 1 and height 2. When you just look at the red triangle and the green triangle, the number of interior points is not changing, but the points on the perimeter is changing. We are adding 2 more points to the perimeter from red to green.
Yeah.
Right. So the formula is still working.
1, 2, 3, 4, 5, 6. Correct. You are adding 2 more points.
So it's like the formula is still valid. We are not adding any interior points, but we are increasing the perimeter points by 2. So it's like still adding an area of 1 extra.
Yeah, true.
So when we go from height to base 2 to height to base 3, now we are having an interior point and we are adding 1 more. So yeah, now we will just count the number of points on the perimeter and the interior over here.
Did we increase any points now? Perimeter point 1, 2, 3, 4, 5. Yeah, we increased 1 point, no? 3, 4, 5, 6. 1, 2, 3, 4, 5. No, we did not, right? We did not increase any perimeter points in that case from green to blue. From height to base 2 to height to base 3. We did not increase any points on the perimeter. We just increase a point inside. Correct?
Yes, correct. So that is, there is 1 point on the perimeter which became an interior point. So it's like the perimeter has lost 1 point, but it has also gained 1 point. So the perimeter is the same, but interior point has increased by 1.
So I'm finding it more convenient to think of it as half a rectangle. So my argument is, if you cut a rectangle into 2 halves along the diagonal, by rotating it, you can make it match, right? You can, they're congruent triangles.
You will still be counting the diagonal points as double, no, Gauri?
We can adjust for that, right? But the increase in area as the perimeter points increase, as the height increases, I'm trying to get it from the rectangle itself.
Okay, so I can see that very high level intuition over here. So imagine that you are having a rectangle where the diagonal does not pass through any points. Right. So the diagonal is like a smooth kind of thing, and all the interior points are now going to be evenly divided into both the triangles.
Okay.
Right. So, but suppose you have the case, like the example that we have, where the diagonal is passing through 2 interior points. So here, when you just like put the area of the rectangle to be area of the 2 triangles, it is just that these 2 the points on the diagonal, which are basically perimeter points for the two triangles, there will be p by 2, p by 2. So effectively, when you add together, they become interior points for the rectangle.
Right.
No, if we are increasing the area by x, like how we did it for rectangle.
If we
Did-
increase the length by x in the case
sorry,
of
if we
rectangle.
increase the base by x, okay,
Length
or base or whatever, base by x. Did we get a formula like how we got for rectangle? As in how much
For
are
a triangle, no, that is what I'm still
how much
working on.
how much are we increasing p and I by with respect to x? No, na?
If we increase the base of a triangle by x, what is the increase in I and
Triangle means I'm talking only right angle triangles right now.
right. What is the increase in I and C? We do not have yet. That's what
with respect to
I'm working on.
Okay, okay.
But I am looking at it from half of a rectangle point of view.
Okay, okay, got it. So that way you will still carry forward your
whatever we did with rectangle.
Whatever we did with that,
Right. So now looking at it with rectangles, I can see how the formula is still working. We will now take the case where the diagonal is not passing through any point. So all the interior points are like all the interior points of the rectangle are the interior
distributed
points of the
evenly.
two triangles. Yes. Right. So now it's like suppose you are having the formula for area of the rectangle. So that is going to be area of rectangle should be interior points of rectangle plus perimeter of rectangle by 2 minus 1, right? You want to show this is equal to the formula applied to the two triangles. So it should be the interior point of triangle plus perimeter by 2 of triangle minus 1, the whole thing times 2.
Wow, nice.
On the left hand side, you just treat the rectangle part. So it will be interior of rectangle plus perimeter of rectangle minus 1. On the right side, yeah, you just do it for the two triangles.
For the triangle that we saw there in the previous geoboard, right?
Yes.
Or I can change this to match that so that we didn't have any points on the diagonal.
Yeah, you can basically change. You can change the background to grid to the dots.
Can you make the background to dots so that we can visibly?
So Ashwin, since two triangles are congruent, you are saying that is twice of these, right?
Yes. So Gauri, you can just complete the formula for the triangle. So it should be I triangle plus P triangle by 2 minus 1.
I triangle.
I triangle plus P triangle by 2
minus 1.
Minus 1, and write it once more because we are doing it for two triangles.
Two triangles.
No, write it once more instead of doing it into 2.
Okay.
So this is what we have to show, right?
We have to show that this is equal to this.
So now you know that interior of the rectangle is the interior of the triangle. So that is, we are assuming the line is not passing through, the diagonal is not passing through any line. So any interior point is either inside either of the two triangles.
Right.
So basically it is the interior of the triangle rectangle divided by 2.
Yes. So you can just cancel those things out.
Right. Yeah. So these two together will be the.
It will not be perimeter of rectangle. It will be perimeter of rectangle minus 2.
Minus 2.
Minus 2. Why minus 2? Here, these 2 points are repeated.
Yes.
Correct.
Yes.
So that will be PR minus 2. And that is what we want. Okay.
Correct.
So we can write area of rectangle AR is equal to IR plus R.
So what we are proving here is that area of this formula works for right triangles also.
But the assumption is means the case we are tackling here is the diagonal is not passing through any.
Correct. Yes, correct. So that is the first case. So if you have the case where the diagonal is not passing through any point, you can see that the formula works for the right triangle.
Wait, the calculation is still not working out for me. So if I add this, I'm going to get I triangle plus I triangle is IR. Okay, that is fine. Then P triangle by 2 plus P triangle by 2 is the same as PR. Okay, so I can replace this by PR by 2 minus 1.
By 2 is equal to P triangle minus 1.
Okay, that works out. Nice. Okay. So now we can see that area of those two triangles given by Pick's formula will indeed be equal to the area of the rectangle. For the case where diagonal does not pass through any of the grid points.
Right. So now we will assume the case where it passes through some points also.
Passes through K points, let's say. So this is including the two endpoints. Or we can take it as excluding and avoid some complication.
Yeah, we'll exclude the
Endpoint.
corners of the rectangle. So these are the K points in the middle, right?
Yeah.
So now it is.
So
basically,
I triangle will be half of I rectangle minus K.
Yeah, that half brackets IR minus K.
Because it's going to both sides.
Yes. That's right.
P triangle will be half of P rectangle. That will give this much plus K plus 1.
Yes. Plus K, whether it's plus 1 or minus 1, let me just check one.
So because we've left out that in K, right?
Correct. Yes, plus 1, correct.
No, not clear. Why plus 1?
So we've defined K as points on diagonal excluding endpoints.
Excluding endpoints, okay.
Excluding the corners.
Right.
So P by 2 will get till here. Now we need to count. We
K
need to
points
add
on the diagonal plus K, na?
plus this one also. So K is the number of points here, excluding the corners. But this one is part of the triangle, but not accounted.
The corners. Okay.
But this is part of triangle, but not.
So when we do PR by 2, we don't get this. This point, this corner we don't get when we do PR by 2.
Okay, not 3 corners, only 2 corners you will get.
Yes.
Yeah. Okay, got it.
So now area of triangle by Pick's theorem is that I triangle plus P triangle by 2 minus 1. So this whole thing, and if we show that twice of that is equivalent to the area of the rectangle by Pick's theorem, then we are done. Let me do 2 times 1 shot.
K gets cancelled.
Will be IR minus K.
Minus half I'm getting. Half
Plus.
I got it as 2 area of triangles is equal to I of R plus PR by 2 minus 1. I got it.
Oh, okay. Great. We'll take it.
Believe me.
Yeah, it is straightforward, Gauri. You will also get it.
Okay, fine. Okay, so it's working for right triangles. So now we need to do generic triangles.
Generic triangles, yes, that's the next step.
If we do generic triangle, we can extend it to, there will still be a missing step. So,
The generic triangles, we can also break it down as like two right triangles.
Right triangles. Okay.
How? So here's my generic
Yeah.
triangle.
Yeah,
By
yeah. Okay.
just
So,
putting a perpendicular, I guess,
uh,
on one of the vertices.
yeah, Gauri, I think now you can go back to the geoboard.
Ashwin, what if the perpendicular is outside the triangle?
Yes,
We'll have
yes.
two
I
different
think that
cases, right?
possibility will be there.
One is inside the triangle or outside the triangle. I mean,
Oh, nice.
Oh, you can always choose another vertex.
another vertex. That is true, but what if we want to
Yeah,
prove it for both the cases?
Yeah. So imagine we are having a triangle where the perimeter has only 3 points. Okay, yeah. So basically, Shubhangi, you are talking about this kind of an obtuse triangle.
Yeah, I think.
Yeah.
But
Yeah.
Oh, okay.
But
in
what?
this case also we can choose another vertex. No, I mean I didn't understand.
No, that is
Oh, no,
true.
no. No. So yeah, I was thinking of some other question. So yeah, we will first answer this case.
Which case, Ashwin? The acute one or obtuse one?
No. The obtuse one. The obtuse one, it's like the area of the obtuse triangle is the area of like the big right triangle minus the smaller
Minus
two right triangles.
the bigger right triangle minus the smaller right triangle will give you the area of required triangle. Okay, correct.
Yeah.
And then we can use our Fick's theorem here directly.
So we've done addition of two triangles equals rectangle that we've done. So it holds that rectangle minus one of the triangles is gives one triangle. So kind of subtraction is working. So we can take that here.
Yeah.
Okay. So does that mean our generic triangle, no matter what the triangle looks like?
No. So yeah, now I think there is one more step. So Gauri, can you make a triangle where only the 3 points are there on the grid? That is, the perimeter consists of only three points. No, can you make like a bigger triangle?
Oh, inside you don't mind, right?
Inside any number of points is okay, but the perimeter should contain only 3 points.
Okay.
This will contain more, Gauri. 6.
It's changing.
How shall I do it?
I think that is the only case, Gauri. This is also.
I can do this.
No. Gauri, what are you doing?
I'm trying to make a triangle with only 3 points on the perimeter.
As big as possible.
No. You just increase the base, so it'll give you like.
But then
more
perimeter will have no more points.
No.
No.
Yeah. Some random thing like this. Yes, this is what I'm talking
about.
Okay.
So, this kind of weird triangle, we have to see how to break it into right triangles.
But we
like
can
this.
always drop a rectangle, right? I mean, perpendicular.
But
Yeah,
the
yeah.
perpendicular of this will not be on a grid point. That was his.
Okay.
Correct.
Okay.
Yeah. So, Gauri, I think we have to look at this kind of a rectangle.
Okay.
So basically, our challenge was only for the rectangle and then the right angle triangle. That's what we did. After that, for any triangle, it becomes generic.
I mean, we have not properly proved it, but this is like the approach that we can see. So once you get the right triangle, you can now get for any triangle.
Oh, I think if we can show that for any generic shape, not just triangle, for any generic shape, if you join two edges, and Pick's theorem holds for polygon 1 and polygon 2, and then you join them together to make a new polygon. So the area will be A1 plus A2. So here we, where the edges are matching, right? So if we can show this for a general shape, I think we are done.
The more if we try to extrapolate the same approach to say any polygon, I'm just thinking aloud. Then the more the complex the polygon is, I mean, the more number of edges and vertices it has, the more number of iterations we'll have to do for finding that rectangle. I mean,
breaking it into triangles.
How, if we have to find the rectangle that encloses that polygon. No, but still.
No. So if we can actually come up with that general proof that if I have a big polygon and I break it into two smaller shapes, and Pick's theorem holds for two smaller shapes, implies it holds for the bigger shape. Suppose you can prove that, then we are done.
Why two only? I mean, how do you understand? I mean, because if it's a complex polygon, then it could be we could be needing more than two smaller shapes, no?
No. So my claim is okay. So Gauri, just like draw a random line for this polygon that you're making.
Like random line.
No, just split that polygon into random two parts. Yeah, just make it into two polygons. Right. Yes, fine. So now, if we are able to show that if you take any shape and if you are splitting it into two different shapes, and if Pick's theorem holds for the two shapes, then it holds for the big shape. Suppose you can prove that, then we are done.
Ashwin, if we are proving for two random shapes, then it's the one and the same thing, right? I mean.
No, I mean, yeah, exactly. That's my question. So here also the two random shapes are absolutely random. Then we could have proved it for the bigger shape also, no?
Yeah, I mean.
No. We're not going to show that it holds for each of these shapes. But we will show that if it holds for this shape and if it holds for this shape, then definitely it will hold for the big shape.
Oh, okay.
This is what we have to show.
Like the composition and decomposition of polygons.
So, for example, what we are showing for the rectangle is that the area of if Pick's theorem is holding for the rectangle, it's holding for the two triangles.
Okay. Yeah.
So so instead of like cutting this rectangle into two triangles, imagine that you are cutting it into say two rectangles or like two trapeziums. Say you're cutting it in that like random way. So we have to show that if Pick's theorem holds for two small shapes, it holds for the big shape also. So the small shape, then we can like break it down further and further so that we come to a triangle or a rectangle or something like that.
Right. Okay. I think that we can do, right? Again, the same way we did for triangles, assuming that there are k dots on that line, on the line that where the two shapes are joined. I think we can do it that way.
Yeah, my approach would be like if you have this weird polygon, I will break it down into triangles. We know that if it works for two shapes, it works for the join of the two shapes, and it works for triangles. So
correct. Yeah.
Still, I mean, it is like a very high level kind of hand wavy proof. It's not a proper proof.
Yeah. And it's working backwards. I mean, we have the formula and we are trying to show that it holds. Even in the original, it may have come from observations and then they tried to show that it is also possible.
Yeah, but I feel there should be like an easier proof.
Mm.
Because this reminds me of that diagonal of a rectangle, right? Passing number of squares along the diagonal.
Yes, yes.
I remember coming up with like a very, very weird, complicated formula, and it turned out to be a simpler formula.
Yeah. Shall we stop here?
Yeah.